So, if you guys saw the last video, uh, that approximation, like, it would be very, like, not good to say that I just found it by plotting masses and things on these graphs. So that's not what I did. Of course, I found the data on net and then tried to imitate it. But how did I get the idea? Why did I try it? Even though like there's no reason why one should do it, right? So why did I do it? In fact, so the thing is, I don't remember things that easily. So I don't remember the mass of elements that are larger. So yeah, and anyway, it's a good exercise to do it. Yeah. So right. So um, I want to give I want to give you some idea on how I did this. So there are like multiple methods of doing it. One of them is just go on the Wikipedia. You will find a semi-empirical formula something um, for the neutron upon proton ratio, and yeah, so that ratio is used in uh, like used in the study of radioactive materials and stuff. Well, that's not what I was doing. I did not have that goal. I was just looking for if there's a formula which I can use directly, and I thought there would be a lot of formula because like people keep on approximating things to simplify everything basically. So I thought, yeah, there must be formula, and there was a semi empirical formula, but it was not the easiest thing to solve on a test. So that's this thing. In fact, this is also like just the approximated form of it. So some guy on Stack Exchange approximated it, and then he said that you can use this if you want a rough estimate. And yeah, so this does fit with the data, uh, right? And this is the thing that I approximated. So this also fits very closely with this, as you can see. Of course, there's like a bit of change over here, like this little thing, but does this even matter? I don't know. And as you go down, it does get more and more like same kind of thing. And as you go up, after a certain point, it like becomes the same. But then if you keep going further, you will see it starts to diverge once again. So this is because this thing is a quadratic equation, sorry, a quadratic expression, and this thing is not quadratic, and there must be some kind of calculus over here that makes this happen, right? So that's okay. And so first in fact I tried to approximate this by using GBT, so the general binomial theorem, and just try to find y in terms of x. But then I realized that x values will be very big, and it's basically impossible to use GBT. So then I changed this. I said, okay, let's find y minus x upon x. What about that value? That value is small, right? But then turns out that's also not very small, because look at this. When this thing is 100, this goes all the way up to, so this guy goes to like 160 or something, right? So if you calculate what y minus x upon x will be, it's 0.6, and that is not a small value. And this graph is only working for these large values, and for small values, who one needs approximations, because you can just memorize stuff, right? It's not that difficult up to 30 maybe. Not that I know all the elements atomic masses till 30. I only know atomic masses of elements that I use very often, right? So till 30, 40, nobody needs a formula anyway. It's only after that this becomes like very tedious to memorize everything. So I thought, okay, this formula kind of resembles this formula, and this is a quadratic expression. So what if I could find like I could prove that a should be very close to 0.006. So I said, okay, so let's consider this function x into 1 plus ax, and let's see if this function resembles like this equation. But then I quickly realized that this will only happen at like one or two values. No, not actually two, it's just one value, because it's only ax. There's only one variable, one equation, so the resemblance will be at only one value, and depending on that value you can change the value of a, right? So you can change your a such that your closeness to this actual graph shifts from, like, let's say from this point to this point. So you can change it. So if I change this to 0.05 for example, then it changes and it goes up. So now, right, so now this thing resembles it as we go somewhere over here, right? So over here it's thick, and that means these are close. If I increase this, let's say I increase this to 0.67, which is what I did for 64, so this will probably resemble a lot at, sorry, not 64, I think 60 or something, right? So when I wanted these two graphs to resemble at x equal to 60, that's why I put this thing over here. So 0.067, that's the calculated value that I got when I took x into 1 plus ax, feed that into this equation, and then put 60 comma 90 into this, right? Yeah, so when I put that into this thing, it omitted, like it gave the value a equal to 0.067 something in front of that. I'm not gonna do that. So it was actually like 0.068 in fact, to be more precise. And now you can see, like, yeah, it's very close in this region. So then you can change this. Then that means if I select my roots, basically, right, so it's a quadratic expression, it will have roots if I set this to a certain value, like, yeah, so x comma y, if this passes through, let's say, 3 x comma y pairs, then I can figure out what kind of quadratic expression will do it, right? So we can figure out from the roots what the quadratic expression should be, and that's exactly what I did. So this graph, so just not have this graph over here. So this graph, this thing, this is for calcium. It's for I think the other thing was z equal to 40, right? So at 20, 40, and the last thing was 80, so mercury. So at mercury, calcium, and at 40, which is, I think it's zirconium or something, right? At these elements, it just resembles perfectly. That is, those were the roots that I chose. So at 20, the y value will be, oh come on, yeah, so the y value, so this is the green graph that we are talking about. So the y value will be exactly 20. So that's because I chose that as one of the points that our quadratic will pass through. 40 will give 90, I think, no, 50, right? So 90 is the total atomic number. Actually it's 91, but then for simplification purposes just consider 90. And 80, that will give, so this line, it will give, it keeps on going, right? So it will give this thing, wait, that's not, 80 should give right, this, which is 120, I think, right? So it gives 120. So that means it, like this thing, it works in this region from 20 all the way till 80, and it works even better when it's close to 40, right? And that's the atomic number of the elements that people can't memorize directly and are also used very often. So I thought, yeah, if I want anything that's of practical utility, I should have this equation to be that approximation, right? Because it actually works for the elements that we want it to work for. So you can have a similar kind of approximation. So pick up any data page, like consider just 3 points, and you can find a quadratic expression that passes through those 3 points. Consider 4 points, you can find a cubic equation. Consider 5 points, you get the idea, right? So this thing is not that accurate, but it's still a very good approximation. So call this thing like 0.07. In fact, that's better. So forget about 6, 5. Let's go to 7 directly, because at 7, this graph, it will resemble this graph, the actual graph, very closely at these values, 40 to 60, and those are elements that we need quite often. And also, like at 80, 100, these values, it will resemble it, but not that closely. So you can find out like average, like estimates of atomic masses if you need that in calculations. Yeah, but not for putting answers into yeah, so not for giving answers actually, because for the answers you need to actually memorize the atomic masses. Still, you have to memorize a lot of stuff. But say like you need the mass number of silver, it's about 100 or something, I don't know, from this graph. So okay, now what was the atomic number of silver? I don't remember that. Fine, but it was okay. Let's just actually Google this, you know, or I could just revise the periodic table, like hydrogen and lithium, beryllium. Fine. Ag, atomic number. It's 47. So 47 should be somewhere over here, right? And that goes up to this value, I think, and that value is, that's not close to 100 at all. So it's close to, oh yeah, so it's just the neutrons that we're talking about. It's close to something bigger than 60. So 60 plus 40, that's 100, and slightly bigger than 100. So its mass number, that is 107.8. That's approximately 108. So does this become 108? I mean, it's like 47 plus 60, let's say it's 65, I don't know, it looks like 65, it is, yeah, right? This is going up directly, and oh, we can just directly do it, right? So 47, that's 62 point something, right? So when you add that, it just becomes 109.436, right? And yeah, so it's close enough to 108. The thing is, it's close to 100, and that's the rough estimate that you will take while calculations, and it works. So the next time you don't remember the atomic, like you don't remember the mass number, but you do remember the atomic number, just gonna put this in there. But then of course you need to remember the atomic number in the first place. Yeah, for that you need to memorize the whole periodic table. So this only works if you know the atomic numbers already. It's just very useless. That's all I can say. But yeah, it's a good result. Like not even a result. Actually, it's not a result. We made this, right? It's not a result of anything. It is the result of me trying to approximate this thing, this beast. So if you know how to approximate this, please give me some idea on how to do it, because I really wanna understand how like approximating this thing will give me these values. And also I just want to find when will this kind of curve, so x into 1 plus ax, like it will resemble this at the most points. So I don't care about the region where it will do it, because it's useless anyway. I just wanna make this resemble it as much as it can. So at in some region, we don't care if that region is practical or not, in some region all of the points, or like approximately all of the points, it should closely resemble those points. So how would we do that? My guess is that it will have to do with the slopes of both of these being equal at that point. At the same time, the values must also be equal. So yeah, that region we can try to find, because 1 plus ax, there's only one variable over here. So you can definitely, and then you can add another variable. So like 1 plus, so you can add another variable x naught, which is the midpoint of that range, for example, or like the point where these intersect in that range, not the midpoint, the point where those intersect. And then at x naught, both of these graphs are the same basically. Yeah, that's what I want to find, a for that kind of thing happening. So you can maybe solve it, but seriously, to the power of 2/3, come on. I don't have that much desire to do it anyway, right? Because this is sufficient. Yeah, this is sufficient. And in fact, 0.05 is better, because this will be used for bigger elements anyway. And then this graph, I didn't explain what this graph is. So this graph is just an approximated, even more approximated form of this guy. And yeah, so I just changed this 240 to 250 basically. And this graph also resembles it. So that's good. I don't know where the roots of this is, like whatever. But yes, it does resemble our original graph, and that's all we need. So yeah, if you have a lot of time at hand, solve this equation. If you have less time at hand, solve this equation. If you have some time in between of that, solve this equation, or this equation. Both are the same. And yeah, I will see you guys in the next video.